Good morning, AP Chem. This is where we left off yesterday with notes, talking about the reaction quotient, QC. Again, the reaction quotient, QC, describes relative concentrations of products and reactants at any given point in time. It's not necessarily at equilibrium, although it can be at equilibrium. So the expression for QC is the same as the expression for Kc, which is the concentration equilibrium constant. And basically anything with a K in front of it is going to be at equilibrium. Anything with Q in front of it can be at any point in the reaction. So again, the way that we find that expression is the same. The concentration of products raised to the power of their stoichiometric coefficient over the concentration of reactants raised to their stoichiometric coefficient power. And again, so remember, we do not include that for things that are in the solid or liquid phase, only gaseous or aqueous phases. So here we have an example. We want to write the expression for the reaction quotient, QC, for this reaction. So first thing I notice is I have zinc solid and chromium solid here, so I will not be including those. My product is going to be zinc bromide. So I will have the concentration of zinc bromide, ZnBr2, to the third power, divided by the concentration of chromium bromide, CrBr3, to the second power. So that should be my expression for the reaction quotient, QC. And there it is. So again, this is not necessarily like the data points that I would plug in here, the numeric concentrations. These might not be the concentrations at equilibrium. So I'm going to go way back in slides here, just kind of show you where you would use K and where you would use Q. And I'm going to use the one with concentration in it. Okay, so my Kc, which occurs at equilibrium, I would plug in the concentration here where it flatlines, because I know that the system has reached equilibrium. If I am, I'm just estimating here, from this point backwards for either one of these, those are the data points I would plug in for QC, because all through here, the concentration is changing, and we have not achieved equilibrium. Okay, so that's really the difference between QC and Kc. It's just whether you are at equilibrium or not. Now I gotta jump back. There we go. So that is our expression for the reaction quotient, QC, for this reaction. Another thing we want to talk about is Kp. So this is also K is going to be at equilibrium. Kp is a pressure constant. So rather than concentration, Kc, equilibrium constant, Kc related to the concentration of reactants and products. Kp relates to the pressure of reactants and products, again at equilibrium, because we're talking about a K value here. So we have, again, stoichiometric coefficients and all of our species involved in the reaction. So we have the pressure of species D and the pressure of species E, both raised to their stoichiometric coefficient power, divided by the pressure of species A times the pressure of species B, both raised to their stoichiometric coefficient power. And this is partial pressure, usually measured in atmospheres. And this gives us a pressure constant. So remember with gases that concentration and pressure are directly proportional to one another. If we increase concentration, we increase pressure. So that's why we can use this for gases. For these, you do need to use rounded brackets, not square brackets. It's just one of those weird things. I don't really have a reason why. I really don't. Usually to remember that, like the rounded brackets, I always think like they're round like balloons, and balloons are gases or filled with gases, and gases have pressure. So that's kind of how I remember that. Anything involving pressure, you're going to be using rounded brackets, not just square brackets. And the expression overall is the same as Kc, where we have the concentration constant, except that we use, again, the partial pressures, not the concentrations. So again, for gases, Kp is often used. The partial pressure is the pressure exerted by that specific gas and that gas only. The partial pressure of all gases in a system will add up to the total pressure in that system. So the sum of those pressures will equal the total pressure. Remember the thou shalt not forget, we do have one equation we need to remember, and that relates the basically partial pressure of water gas versus the partial pressure of another gas that we create. If we have 1 mole of one type of gas, it will exert the same pressure as 1 mole of a different type of gas under the same conditions of volume and temperature. So if you remember at STP, there's a standard temperature and pressure. There's a relationship between the volume of gas and the moles that is in that gas. Do you want to come say hi, Polly? Here's my cat. Break from chemistry. Polly, say hi. Do you like chemistry? Huh? She's more of a physics person. You can see her do cat physics anytime she tries to jump from anywhere. There you go. I'm going to give it back to you. Anyhow, so at standard temperature and pressure, remember that 1 mole of gas for any gas has a volume of 22.4 liters. So that's why we can relate pressure of gas with moles of gas. So if we have 1 mole of gas, any type of gas, it will exert the same pressure as a mole of a different type of gas under the same conditions of volume and temperature. 2 moles of gas would then exert twice as much pressure. 3 moles would be 3 times, and so on. So here we have an equilibrium constant with, this time using pressure. So here all species are gases, so we can use their pressures. We're still going to have reactants on the bottom and products on the top, raised to their stoichiometric coefficients. This time, be sure again that you use round brackets in the Kp expression. So for your Kp expression, you should end up with the pressure of NaCl, our product, to the second power over the pressure of NO2 gas to the second power times the pressure of Cl2 gas. Okay, there we go. We can also use a reaction quotient Qp that describes the relative partial pressures of products and reactants, this time at any given point in the reaction. So it's related to Kp, it's the same idea, the same overall expression, but this time again, we can use this Qp at any point in time, whereas Kp is only at equilibrium. We have to be in equilibrium to find the Kp, the equilibrium pressure constant. But it's the same exact setup. So if we have this reaction, maybe we're finding the Qp for the very beginning of the reaction. To set up our skeletal equation, or what our expression would look like, that little error message, we have 2 solids here. So we are only going to be focusing on our 2 gaseous products. So we will take the pressure of H2O gas times the pressure of CO2 gas. And both of these have a coefficient of 1, so we do not put anything in the power of those. And again, we're going to use rounded brackets. Since all of our reactants, or one reactant, is solid, we do not have anything in the denominator there. Okay, so that is units 7.1 through 7.3. I do have a worksheet for you to work on related to this section that you can work on, obviously. We will be applying more numbers to these expressions, so you may actually calculate eventually the equilibrium Kp, Kc, or the reaction quotient Q, Qp, or Qc. So we will get to that point, which is just pretty much plug and chug from here. Okay, so I'll post that worksheet and you can use the rest of class time to get started on it. Have a great day.